Today we're going to talk about precipitation reactions. And we can see here some examples. If we mix certain chemicals that are clear solutions, like silver nitrate and potassium chloride, these will react and form. We're going to place AQ to show that these are in solution, so these will be clear solution. They will form potassium nitrate, which is still a clear liquid, and silver chloride. And silver chloride will actually precipitate, and what we will see is something similar to this picture. So how can we predict if when we mix two chemicals, a precipitate will form or not? Here we have a list of ionic compounds. When we look at ionic compounds, we know that they're composed by a metal and a non-metal or a polyatomic ion. In order to determine if these compounds are soluble or not, we can use a table called that of the solubility rules. So we can see that if a compound contains sodium, it is completely soluble, and there are no exceptions to this rule. So we can immediately see that sodium sulfate is in fact a soluble compound. So we will mark it as AQ. When it comes to lead bromide, we can see that the solubility rules tell us that compounds that contain a bromide ion are generally soluble unless, these are the exceptions, they contain silver, mercury, or lead. In this case, our compound contains lead, which makes it insoluble. When a compound is insoluble, we're going to mark it as S. This sometimes creates some confusion because S is confused with soluble, but S stands for solid because this letter indicates the phase in which our chemical is in and not its properties. So S for solid, which makes it insoluble. Silver nitrate, we can look again at our table and we can see anything that contains a nitrate ion is soluble, and there are no exceptions to this rule. So silver nitrate will be AQ. For barium sulfate, we can look at the sulfate ion row, and we can see that compounds that contain sulfate are soluble unless they contain silver, mercury, lead, calcium, strontium, or barium, which means that our barium sulfate will be insoluble, and so we will mark it with S. These in general can help us determine if mixing two chemicals will create a precipitate or not. Say, for example, we want to mix sodium sulfate and barium chloride. First of all, we need to predict the products of this reaction. To do that, we're going to look at the metal part, leave it in place, so we're going to write it as is, and we're not going to write the stoichiometric coefficients for the moment. And then we're going to switch the two anions. So we're going to write Cl and SO4. So these will be our products. Once we have written that, we want to make sure that the formula we wrote are correct. So we know that sodium forms a +1 ion and chlorine forms a -1 ion. So this compound is neutral, so the formula for sodium chloride is correct. Barium forms a +2 ion, while the sulfate ion has a -2 charge. So this formula is also correct because the two charges cancel out and the compound is neutral. We want to now balance our equation, and we notice that we have 2 sodium and 2 chlorine, which means that we need to add a 2 in front. Once our equation is balanced and the products are determined with the correct formula, we can now determine if these are in aqueous solution, hence soluble, or solids, insoluble compounds. We looked at the table before and we saw that anything that contains sodium or any metal from the group 1 it will be soluble. So we can directly mark these two compounds as an aqueous solution. Barium chloride, we can look again at our table, find the chloride ion, and see that there are exceptions, but the barium is not an exception to the rule. Hence, barium chloride is soluble, and we can mark this as AQ. For the barium sulfate, we can locate the sulfate line, and we can see that our barium sulfate is insoluble. So we can write this as solid. We have now determined that this is a precipitation reaction because we mix two clear solutions and we produce a solid. Once we have written our precipitation reaction in the molecular form, we may reflect upon the fact that ionic compounds will ionize when put in water if they are soluble, which means that these compounds will not exist as molecules, but they will exist as ions, which means that more correctly we should write this reaction in the form of ions. So we should now split all our compounds and write them as ions. All ions will be indicated as being in the aqueous state. When it comes to the writing of the compound that is a solid, now because it's a solid, this does not exist as ions. So this compound will not dissociate and can be written exactly as is. This equation is called the total ionic equation. And when we write a total ionic equation, we may notice that we have ions that appear identical, so chemical species that are identical from between the reactants and the products. Likewise, in a general equation, mathematical equation, where x's can cancel out if they are identical, this can be done in a chemical equation. So these pieces can be canceled out because they are the same. And we are left with an equation which is called the net ionic equation, and we can write it as what is left over, SO4 2 minus. So that is the net ionic equation. The net ionic equation represents the only reaction that is happening in our container. The ions that we canceled out do not participate into the reaction, and they're called spectator ions. So the spectator ions in this reaction are Na plus and Cl minus. Let's look at one more example, the reaction between lead nitrate and calcium chloride. The first thing we want to do is write the products of this reaction. As said before, we're going to leave the metals in place, and then we're going to switch the two non-metal portions. We're not going to write the stoichiometric coefficients for the moment for the two anions. Now, we can see that lead has a +2 charge, chlorine has a -1 charge, which means we need to multiply this by 2 to obtain a neutral compound, which means this will require Cl2. For the calcium nitrate, calcium has a +2 charge, nitrate has a -1 charge, so again we need to multiply this by 2 in order to obtain a neutral compound. In terms of the state in which they're in, the compounds that contain nitrate ions always are soluble, and there are no exceptions to this rule. So we can write this as AQ, both of them. For the calcium chloride and the lead chloride, according to our solubility table, we can look at it and we can see that if a chloride is present as an anion, the exception are sulfur, mercury, and lead, which means that calcium chloride is soluble and can be written as AQ, but lead chloride is insoluble, hence we'll have the S for solid. We now want to write this equation as a total ionic equation. To do that, we're going to split all the compounds that are AQ in ions, as they will ionize in solution. You want to make sure that when you write your ionic equation, you do not forget to write the charges. Writing Cl or Cl minus is not the same thing. When we write the lead chloride, we said it's a solid, so this will be written without forming ions because it will not. And then we can write our last compound. And all our ions will have aqueous solution symbol. Once we have done that, we can see that there are spectator ions which are identical between the reactants and the products. So these can cancel out, and these can cancel out. Notice that chlorine and chlorine do not cancel out. This is a chloride ion. This is not. So these are not the same species. These are the same species because they're both calcium ions. So we're not just looking at the symbol of the element, we're looking at its charge. So if it's an ion or if it's part of a molecule, and we're looking at the phase as well. So they must be identical in all parts before they can be called spectator ions. So the net ionic equation for this reaction, which is the only reaction that occurs in this solution, is going to be Pb2 plus AQ plus 2Cl minus AQ that form lead chloride solid. And the spectator ions are the ones we canceled out. So nitrate ion and chloride ion.